Good afternoon, and thank you for joining. There is an awesome talk from Jurgen in the main auditorium, and you've decided to be here, so we are grateful for this. Who's attending Spring I/O for the first time? Oh, wow, nice. We are here for the second time and enjoying a lot, and this talk is also special because we've known each other for 10 years. We had our first pair programming session in 2015. And then it means a lot for us at this talk. Who's having fun with Java for more than 10 years? Nice. And who's having fun with Java for more than 20 years?
Ooh.
Nice.
Wow.
Let's go. Since this year we are celebrating 3 years of Java. Super nice. And okay, hope you'll enjoy the next period with us. And without further ado, let's start.
Okay, thank you. Good afternoon. Let's start with something that we all love to hate. The cloud costs. I think that's why we are here, right? We all thought when the cloud came about, it's that magical thing that is fast, scalable, and cheap. But it was anything but cheap. State of the cloud report from Flexera says that organizations are spending close to 600 billion last year, and this year it's only increasing. And here is the kicker, actually. The spite of them increasing, they are over 17% over budget. And let's start with a short quiz. How many of you are, what do you guys think is the average CPU utilization in Kubernetes? Maybe less than 50% can raise your hands. Less than 25%? Ooh, nice.
Nice. Is it 90% utilization on average or not?
If it was 90, probably we wouldn't have people here. Anyhow, it's approximately 10%. It's basically like we roll out massive clusters and we let almost 90% of them idle. That's basically, it's like we roll it out and then it's like on paid vacation. And what's even more intriguing is even in large clusters, more than 1,000 CPUs, we only have on average about 17% utilization. Now, whenever there is a challenge, I mean, there is also an opportunity, right? What happens if we can pull back some of those into savings and improve on utilization, thereby also improve on cost? We don't have to be massive. It doesn't have to be 50% or 80% or maybe even 40%. Even if we improve by twice, which is still only 20%, we would save a lot of cost. So that's what this session is about. We'll try to give practical tips to improve cost, but also look into the system design. That brings us into the goal of today, which is basically two simple goals. Goal one is to understand the design strategies that would influence basically cost, balancing the trade-offs.
And then goal two, to look into the development best practices. Yeah, most of the patterns are well known by you. And then we can tell exactly what we have applied, what did work and what did not. And first, let's present ourselves. I'm Laurentiu Marinescu, full stack software engineer. I like to call myself a problem solver and passionate about software craftsmanship in general and any new tech, and an advocate of pair programming. This is how you see me in the office. And a bouldering lover. Who likes bouldering here? Any fans?
Whoa.
Wow, that's super cool. And Barcelona is a known place for bouldering gyms and climbing places. So then let's talk afterwards about.
I'm Ajith. I'm a system engineer at ASML. I drive data platform requirements and strategy. Outside of work, these days I'm mainly interested in AI. I think the opportunities are massive. If you are interested as well, happy to connect offline. So proceeding, just revisiting the storyline. Basically, we know that organizations spend a lot on cloud. We know that they also want to control it, obviously, But despite them trying to control it, 17% reported that they are over budget. And what's even more surprising is that on one side we roll out massive clusters which are expensive. We also want to control the budget, but on top of trying to control it, we still only effectively utilize 10% of them. So it's like we roll out and then majority of them just sit idle. But there should be something here, right? I mean, I trust humanity. Collectively, we can't be that ineffective. There should be something going on. So it couldn't be that simple. If it was simple, it wouldn't be at 10%, despite us trying to control it to be better. So what are the things that would affect? Let's start with that. So here, the color contrast is not that much, but I'm trying to give a simulated example of basically two simple nodes. The reality could be quite different. We would have a massive amount of nodes, but at least these two would help us to bring home the point. So basically, we have two nodes, node 1 and 2, with 5 containers in total. Just assume everything is equal, both the nodes have identical spec. And basically, in this case, we have just packed in as much as possible without having to roll out further, which actually saves cost. But the question is, of course, we saved some cost, right? Because we didn't have to roll out much. But then what is actually the cost? Is it only about money? What are the consequences of this? Let's play with some scenarios as examples. Scenario 1 is, if we want to upgrade, for example, let's assume container 1 and 4 belong to the same release and we want to roll out our next release. What really happens in this case is we wouldn't be able to roll it out both at once. So it has to be sequential, and that's already pushing it, because at least in node 1 we only have 25% capacity left. And if you want to have zero downtime upgrades, that's actually impossible, at least for the heavyweight container. So these are very simple consequences, but quite large in terms of production. So if you want to scale as well, let's assume that container 3 belongs to app-foo. App-foo suddenly sees increasing demand, and we want to scale out, but we simply can't because lack of resources. Actually, in cloud, if it's not on-premise, you can come up with heuristics where you can find, as long as the workload is a bit deterministic, you can make out that, okay, I'm going to scale out, this is the workload patterns, I'm going to expect these kind of demands, so let me scale out. But in our case, we'll see that also later, we are on-premise. That means we simply cannot scale out on demand instantly. There is a long lead time. So these are the things that would affect. Again, going on, in case if we did scale out, and then if there are, we also have to account for failures and crashes. So if there are multiple instances of container 3, if one of them misbehaves, we don't even have enough room. And to top it off, thinking of just node failures, right? In this example, like I said, it's completely made up. But in this case, if node 1 goes down, we immediately lose 3 containers, and the rest of them can't even spin up. So thereby, we lose half of them. If those are critical workloads, then it's gone. Now, if we just extrapolate a bit further, if both those nodes are in the same zone, the complete system is down, which is not a nice scenario. We could also say that, okay, so obviously these nodes would be distributed. Node 1 would be in zone 1, node 2 would be in zone 2, but even in that case, half the workload is gone. So ideally, what we would need is to back it up. If it's a very mission critical platform or a system, then we need to ideally be running hand in hand, both of them. In case one zone goes down, the other can handle the workload instantly. If we take these precautions, obviously we will never reach, let's say, 70 or 80%, because in this case I'm already pushing it quite extreme theoretically, and in theory it wouldn't hold. And so far, if you notice, I didn't even talk about the usage, the real usage of the nodes. So for example, the dark blue, I'm not sure if the contrast is that high, but basically the filled out part, assuming that at least the containers that we rolled out are 75% in usage, that already reduced the utilization by 25%. So just to make it a bit more practical, let's throw away all the things here. We only have 2 containers. Even targeting 50% utilization in this part would still not guarantee upgrades if one of the node fails, which is a very common scenario. So if we extrapolate all of these things, actually we are not after utilization, we are actually after efficiency, balancing all the trade-offs and the costs. So that's what we are after. But to further look into this and what are the things that we actually did run into, but also that we managed to solve, with some practical examples, let's zoom out a bit, try to understand our own landscape that will help you to put context into it. All right. Let's start with another short quiz. What do you guys think that is? I can assure you it's not some alien machine that's producing more aliens. It's actually a lithography machine of ASML. What you see here flashing is actually a laser light that's being printed on with pinpoint accuracy on a rapidly moving stage, like a circular disk. We call them wafers. It is so accurate that it actually controls processes at nanometer scale. Now, just to give an example of things at nanometer scale, imagine that I decide to shave my beard, and then I pick up the blade, and by the time I touch my skin, the beard would have already grown by 1 nanometer. It's that insane, and to think that we humans have produced machines that can control processes at that scale, it's simply mind-blowing. I've done this same talk multiple times, but every single time I talk about this, it's always mind-blowing. But it's not about lithography; it's about cloud costs. So let's move on. But if you're interested to know more, happy to connect offline. So the point is, at nanometer scale, things are never as it seems to be, or we can't really get 100% control. So what we have is a list of applications. These are mission-critical applications that we need to host on top of data platform, and that's where we come in. So we host a list of applications. There are about 50 products that integrates into the platform, and these products are super important. So let's look into some of the technologies that we use. Basically, we use all sorts, all major ones. So 90% of our workload is in Java. We also use Kafka, for example, messaging. We used to be in DCOS as an orchestrator. These days, we moved into Kubernetes.
Heavy users of Kafka.
Heavy users of Kafka, very important. But let's move on. So just to put things into context, I want to just briefly touch on the topology of our platform. Basically, our focus today is mostly into the compute and the edge nodes. We also have storage, but we are not going to look into that. But this is still an important picture because we can put all sorts of efforts in the first few things, but majority of your workload is in the storage. We still are not going to improve much. In our case, it was 50-50 distributed, and so all the containers are running in these 2 node groups, and we have different workloads of varying sizes, varying specs, varying needs.
Take into account this is a super simplified cluster topology.
Yes, indeed. Super simplified. Reality is quite different. Now, what are the key challenges that we face in our platform? The first thing is the workloads are very diverse, and both critical and non-critical applications coexist in the same platform to the infrastructure layer. So that means also the storage itself is being shared with both critical and non-critical applications. For example, the durability for the critical applications would be very high. We can't afford to lose the data, but not so high for non-criticals. As I said multiple times, some of these are so critical that 10 minutes of downtime would potentially result in millions. So it's super important that they are always available and in very high usage. And on-premise cluster we run, so this is one of the important points. So on cloud we have a bit more leeway, bit more flexibility, freedom to expand things at scale. But when you are on-premise, these are physical hardware, there is physical limit, and then the lead time to scalability would be quite high. So sometimes we even have as high as 6 months. So we got to predict well in advance to make sure that we have dimensioned the cluster properly.
Who's dealing with the on-prem clusters in production? All right.
That's more than at least what I expected. And all of these combinations actually resulted in underutilization of the cluster, obviously. So to go further, Laurentiu will give select examples of these to proceed further, and then how did we take steps to solve that.
Indeed. Buckle up for the next section. Let's zoom in a bit. And we have 3 types of applications mainly. We have applications that have different execution patterns. We have applications that do not peak at the same time, of course, on a certain node. And we have applications with a non-deterministic behavior. And depends on which type of applications they are. If they are CPU intensive, memory intensive, IO intensive, is making the resource management quite complex for the CPU utilization. And next we're going to look at 3 observations, again main ones, that we observe with our workloads in our clusters. And as Ajith mentioned earlier, underutilization. It's one of our primary issue. If you can see here at the graph, what is actually this app doing? So most of the time is idle, and then around 8:33, it's reaching 50% of the CPU allocated. Yeah, it's heavily underutilized. Then you may wonder, okay, but why do we have it deploy so early? And that's a catch. Depending on the user customer processes, we cannot predict and form a pattern on how they use it. So therefore, we need to deploy the applications, as Ajith mentioned before, to accommodate for this. And then the second observation that we have, that's a classic one. We have applications that are not optimized and they throttle. And then we allocate less than what actually is needed for these applications. And the third observation is, and that's in contrast with the first 2, we have app saturation. So then we have applications that, let's say, are high intensive on IO, and then all the threads are busy, and then they receive new requests, and they are either waiting or they are delayed, and then this will affect the response time of the app, which will impact the SLO of the clients, essentially. So then further, we're going to expand on these 3 observations. And if we zoom in into the Java Spring Boot apps, again, most of you aware of these issues. We deal with blocking IO operations heavily. Yeah, we still have slow database queries. And this is a fun one. Yeah, we observe frequent or long GC pauses. Next, I'm going to explain on what we did to improve on the GC part. And then, of course, we also have thread contention, depending on how we define the locks. And, of course, Java applications are by nature CPU hungry. We are dealing with a multi-threaded environment, and this can lead to the CPU starvation when a container doesn't get enough resources, and then it will cause low performance, and to CPU overcommit, when a container uses more CPU than allocated, causing throttling, and then can lead to node crashes, or even further, zone crashes, and even the whole cluster. And next, I want to go a bit into the theoretical part. This is a key takeaway, which was a shift for us when we look in how to improve the CPU utilization. And of course, we are dealing with orchestration platform, but we need to understand what's happening at the OS level. And then, very simple, how Linux will calculate the CPUs. If you go there on the node, you can run lscpu, or you can go to proc CPU info, and then it will tell you an absolute number of the CPUs. And this is computed starting with the motherboard, since we are heavily involved into the chips manufacturing. We have the sockets physically on the motherboard, then they have 1 or multiple cores, and then each core can have 1 or 2 threads, depending if hyper-thread environment is used or not. And then we get to this number, 16. Okay, beautiful. But the catch is that at the Linux level, CPU is in time. So this is how Linux thinks about. CPU in time, and that's essential. So then your Java app, when you configure it, it doesn't get an absolute number. It will get a time slot. And this was the key for us on how to further adjust at the application level. And then, of course, going very short here, this is an in-depth domain. And yeah, you can research. There are plenty of better talks about. But at the Linux level, there are multiple schedulers. And then the default one that will look is a completely fair scheduler. What are the schedulers? They are the traffic police for deciding which processes that will get the CPU and when to get it. And then I will try to explain super simple the completely fair scheduler. And after this talk, I hope all of you'll be aware, okay, this is how it works at the Linux level, regardless of Kubernetes. And then if we have 3 tasks, to keep it simple in an isolated environment, task A that takes 25 milliseconds, task B that takes also 25 milliseconds, and task C that takes 100 milliseconds. Then completely fair scheduler will have to schedule these 3 tasks. And then see how it will do it. If it will utilize the CPU time, by the way, CPU at the Linux level works also in periods, and by default, one period is 100 milliseconds. And let's say if it allocates the whole 100 milliseconds for task C, then it will be unfair for the task A and task B. So then, how will actually completely fair scheduler do it? We'll try to schedule the smallest task first, and then each task should get a fair amount. So remember, 25, 25, 100. So then we can see that it will finish with task A and task B, and then it will complete with task C in the second period. That's essential to understand how the absolute numbers are mapped to the CPU time. Of course, this is a whole domain that I will invite you to explore. Behind completely fair scheduler is using a red-black tree. For the queue, they assign a virtual time. The virtual runtime is based on already given CPU time that was given by Linux. I'm going at the surface here. Please check it out. But this is the shift that we need to take into account for the further slides. And then if we look at the Kubernetes level, that's easy, right? We have the CPU request. And at the Kubernetes level, this is used to guarantee the CPU on one of the available nodes. That's great. But actually at the host level, this number is only used as a relative weight. That's the only reason why on how CPU request is used at the Linux level. So then if there is competition between tasks, it will define a certain weight. And later we'll explain how this weight is being calculated. And then the limits, it's simple. The container cannot use more than the configured limit. And of course, if it will try to use more, then it will lead to CPU throttling. And if there is no limit, then it can consume all the CPU in a node. And you know that there are controversial discussions about to set or not to set limits. We'll also talk in the next slides about. But I want to map it, this CPU request and limit. Again, remember the numbers. So at the Kubernetes level, we define one CPU will equals to 100 milli-CPU, but then we need to translate it to the Linux level. And then kernel has a feature called C groups that will basically try to isolate the processes and allocate the resources in a nice way. And then we have 2 versions, the C group V1 and C group V2. V1 is since 2007 and V2 is since 2016. And if we look at the CPU request, what actually is being set at the Linux level are the CPU shares. So then let's say we have one CPU request, then we get 1000 milli-CPU multiplied by 1024 shares. One CPU represents 1024 shares, and then divided by 1000. And then the CPU limit is calculated as multiplication between the quota and the period, which I have explained earlier is 100 milliseconds. And then it will get a time. For example, if we define it, the limit also one CPU, then it will actually translate into 100% CPU. So these are the key metrics that we need to take into account, and then we can zoom in at the application level. And this is how it looks at the node. If you go there into the C group and then into the kubepods C group, you can see based on quality of service of Kubernetes, there are 3 types of pods: burstable, best effort, and guaranteed pods. So you see the guaranteed pods are at the same level with burstable and best effort. And if Linux will have to decide the weight between a burstable pod and a guaranteed pod, the guaranteed pod will get more weight. And again, that's crucial to understand. on which type of pods do you define for your applications. So then it will go in hierarchical mode, and then will compete, all the childs will compete at the same level to get CPU time. And now let's have some simple examples. And again, this should complete the loop. I have 3 examples to understand how it works in CPU time. So let's say that we have a pod A, and we have a CPU request. This is one CPU. For this, let's consider it an isolated environment. There is no competition. And we have, so then it doesn't matter, the CPU request, frankly. And then we have a task that takes 400 milliseconds of CPU time. But let's say we deploy it on a node where we have 4 CPUs. So when we do the, let's say, API request, actually the response time will be 100, because can utilize all the available CPU on the node. Now we may think, yeah, but based on our SLO, we are not happy with this response time, so we want to maybe increase it. What do? We try to scale out. This will be the first thought to do it. But then actually if we scale out, you can see that the time reduces in half. So then the response time for each pod is 200 milliseconds. So then already we can see that maybe it's not the best approach to go into the horizontal scaling. And then I have a third scenario, and this is very important. If we define a limit and it's too low, and then in this case we have a task of 100 milliseconds, and then the limit is half of CPU, you see that each pod will get half of the period, and then there will be idle CPU, and for the next period will complete the task. But this actually translates in throttling. This is what's happening at the CPU level. These 3 scenarios are essential to see how the CPU time is being used. And then, okay, how to solve it? And then concretely what we did on our clusters. First, we need to understand the app specification and behavior. We need to rely on app SLOs, but not only the generic ones. We need to look into what's specific for our app, and then decide based on this. The second most important, what we recommend, is to look at the number of threads for your app. And we're going to see later on how we decide on this. And then, of course, the number of requests, response times, and then the task duration. And what did we do? So we need to set a baseline. You can see on the right side there, this is a representation of how the utilization look on one of our nodes. Actually, what we did in practice, we defined some pods called CPU eaters. They will just eat the resource up to, you see there, 61%, in order to deploy our container, and then we start with a single instance, and then start to profile it, and see, okay, how it's behaving. And yeah, what's essential for the Java applications, we need to take into account for the warm-up phase until it reaches the best performance. And then we actually know, okay, what is the utilization, and we need to agree, okay, what's the realistic worst use case, of course. And then what we did, yeah, we have a Java Spring Boot app, then we use Micrometer for the metrics, beautiful. We integrated with Prometheus. These are the Prometheus metrics that we look for the CPU utilization, so primarily the CPU usage in seconds. Then we look for the periods, and then we look for the throttle periods and throttle in seconds. And then, okay, we try to plot this. And here on the top right, we have multiple profiles. These are very small apps. But the point here is, for the case, for the TS and WS, you see that the request and limit are the same, super small. And then it will throttle. It doesn't have enough CPU. And then if we increase the limit, then you can see that it will actually reach the usage up to 0.5. So then it will lead to better performance. And if we look also from the startup time perspective, because this is actually an interesting one, only by setting a higher limit, our apps decreased, the startup time decreased from 100 plus seconds to 15 seconds. And here is where the fun part starts on how we decide if to set a CPU limit or not to set it. And what we actually did to allocate the CPU, because okay, we did multiple of iterations. Yeah, it's not rocket science. We did the binary search. We have an SLO. Let's say that, yeah, in this case, it needs to take 7 seconds, the duration of the job. And then we'll look at how we'll going to behave, given if we define first 2, and then of course it will be within the SLO, and then we'll try to go for 1, oh, it's less. Then we'll go with 1.5, and then 125, we can even go further, 1.1 or yeah, 1.2, but this is to get an idea on how we decide for each container, okay, what's the needed CPU. And then what's very important, Afterwards, we need to monitor, adjust, and react. So we need to continuously rely on the results analysis in the monitoring dashboard. And then, of course, yeah, we can have multiple ways to do this. Different type of alerts or monitoring dashboards. And then concretely on the steps. And this you'll recognize very well. Then the first one is super easy. We have to do the LCM upgrades. There is no other way, and there is a significant improvement using Java 21 and Spring Boot 3.4. And then, of course, we want to leverage virtual threads. Yeah, that's fun, because virtual threads are meant for the heavy I/O services. But that's not enough. Even for heavy I/O services, it depends on the number of requests towards that application. Because we observe for some of our apps, yeah, it doesn't make any sense to rely on the virtual threads. But if we already do this, then we have a significant improvement. So remember, previously we have the startup time of 15 seconds. Now, next, on top of this, if we apply the AOT processing, and then we try to go for the native, we can reduce it even further. Now, concretely, for native, it didn't work well for us. We did not feel enough confidence to go in production with the native images. However, we still kept enabled the Spring AOT processing. And then on top of this, we used another nice feature, which is available already in JVM for a while ago. Probably you are using it in your JVM, the app CDS, so then the class data sharing. And with Spring Boot 3.3, then we can use it for the Spring Boot applications, which means also the class data sharing can be used for Spring Boot libraries. And if you see there, we have the startup time at around 8.5 seconds with only AOT. And then if we do the app CDS, we can reduce it further to under 5 seconds. And this will translate into a significant gain. We are super excited about the next step, which is the AOT class loading. And yeah, hope we can leverage this as well fully.
One more point on the startup time. So the for some applications which have very tight latency, let's assume 100 seconds. The reduction just in startup time itself enabled us for many and opened up many other opportunities, because if you have tight latency, you really need to account for crashes so that you have backup instances always running, even though they are mostly idle, because you just can't afford to have losing momentum in terms of crashes. But then by reducing the startup time, you know that given in the moment of crash, you are up and available, for example, in 20 seconds or so, which you can account for. So we had varying workloads where we could also apply this part.
Indeed, and this will have a significant impact on the CPU in the end. And the third step, deciding on which servlet container to use. Yeah, based on our measurements, we decided that Undertow is the one to go. So out of the three main ones, Undertow, Jetty, and Tomcat, in terms of performance, yeah, Undertow has better CPU usage. For our KPIs, better performance. And for memory, it is using more memory than Jetty, but Tomcat's still using more than Undertow. So then this was the right balance for us. And this is an example with 8 worker threads, yeah, super small. And this is tightly coupled with a graceful shutdown from functionality from Spring Boot. The first step, the fourth step, this is essential one. Do not rely on the JVM defaults. So then for the CPU, set the active processor count, especially in the containerized environments. What is this number? It specifies the number of CPUs available at the system. This is what JVM sees it. And if we don't set it, with the latest Java versions, it will rely on the CPU shares, which is the CPU request. And then is the question, do we want to rely on this? If we set the limit, of course, the number should be the same as the CPU limit. So then do not rely on the defaults and take control of the number of CPUs, because the CPUs are then used for any thread pool, or for the garbage collector, or for the JIT compilation. So then take control over this. And you can check, of course, on the JVM ergonomics. And again, there are better talks about. I encourage you, please have a look on how to get the best performance. And then we look at the GCs. So I put there the 5 GCs and excluded CMS, because that is deprecated since Java 14. But then let me ask you a question, and it should be a straightforward one. what do you think is the default garbage collector for Java versions higher than 9? Just shout out. Nice. That's always the answer, isn't it, for the simple questions? It depends. Indeed, if we have a JVM with less than 2 CPU, or if we have a JVM with less than 1,792, the default garbage collector is the serial GC. So then consider this for your applications. If the applications are small, maybe G1 is not the right garbage collector to use it. And then decide on the garbage collector and then fine-tune it. As I will give you a concrete example from our case. Yeah, we define and fine-tune G1 GC for one of our apps, which was using a significant amount of CPU. And what do we do as developers? Yeah, we try to copy-paste it also for other workloads. And then we realized, oh, but these are smaller ones. And also for those that are big, of the same size, maybe G1 is not the best one. Maybe you should look into the parallel GC or to the ZGC, depending also on other factors like latency. So then spend time and set the GC and fine-tune the JVM params. This is crucial. All right, and then on the next step, yeah, this goes hand in hand. Use async, and then we heavily use scheduled tasks from Spring Boot for the long-running threads and also for the non-blocking ones. Rely on this. And then take control of the thread pools. Define them. And yeah, it's best for the CPU usage to use the same number of CPU cores available, and then for the I/O threads, then try to use even 2 times more or even more. And then if we look now at the cluster level, that's an interesting scenario. What we did, we set the request for the normal usage. And then we also set very high limits. But then if you check it, there will be the dilemma, should I put the limits? Should I not set the limits? That's actually, again, a controversial question. We set it because we have critical applications and we cannot afford for one application to utilize the whole node availability. And then we can look into techniques like CPU bursting or dynamic resource allocation or either resource reclamation. But then, to keep it short, in our case, we set the request for normal usage, even maybe less than normal, and then we set very high limits. So then, yes, we still set the limits. And then, what we also have some nice applications already optimized. 100% CPU usage does not mean bad usage. So we need to take a look and check if we have starvation, and we need to control again the threads per instance. If we have the right number of threads, and then okay, CPU stays in 100, maybe it's not bad. And what we try to aim is for 80% resource utilization. Yeah, this is quite an ambition, considering that we are way lower than 80%. And then if all the applications peak at the same time, then we can still have 20% buffer to accommodate for. And now to go further, at the cluster level, yeah, we could use Kubernetes cluster autoscaler, but actually we cannot because we are on-prem, so that's not an option for us. And then what we can leverage instead? We can look into the horizontal pod autoscaler, but we saw it earlier. Maybe it's not the best idea to use HPA. And if we want to use it, because we have scenarios where we do use it, do not rely on the CPU utilization. Rely on the specific metrics of your app. For example, number of threads, or number of connections to that application, and then you'll scale it out or in better. But then in our case, it's not enough to use HPA because we need to have the activation phase from 0 to 1, then 0 instances to 1 instances, and that is where we leverage KEDA, and for the scaling phase, we rely on HPA. And then, yeah, KEDA can be configured with a tolerance. When do we decide to increase the number of instances? You can see that on the right. Actually, this is a real example. We have the min replica count 2, and then the max replica count 4. So then we try to control the max replica count, because again, we are in an on-prem cluster, and we already know upfront the number of nodes available. And then, of course, we can look into the vertical pod autoscaler. But right now with Kubernetes, we cannot achieve with the vertical pod autoscaler the in-place scaling, in-place vertical scaling. However, since 1.23, we actually have the in-place vertical pod scaling. So then if we have an app that has critical traffic, we can do a kubectl patch pod and then increase the limits or the request. So this is now available. That's a feature that is now in beta. So before in 1.27 it was in alpha, and maybe you remember the other feature from Kubernetes where we can boost the startup of the pods, especially for the Java applications. So let's say with a cluster policy, you can define to use more CPU for the startup, and then, okay, it will reduce to the regular workload. So then this is a pretty fun one, but cannot be used with autoscaler as of now. So if you want to use it with vertical pod autoscaler, then you need something custom in between. And okay, this is it with what we have applied. I will give the floor to Ajith to present the success story.
Thank you. Very, very energetic. Thank you. So far we looked into how we did take implementation steps to improve utilization, thereby improving the cost. Now I'm going to talk about one success story that we took action from the cluster perspective. We did a series of things with different improvement options, but nothing was as impactful as this one. The complexity here is not in terms of technical challenges, but mainly in terms of the consequences of the fundamental assumptions that we took. And I also wanted to show this because I know that the industry is a bit in splits with this, and how simple it is to implement, provided you accept the assumptions. So what we did was we have already established that we have mission critical applications where a delay would potentially cause lots of issues in terms of operations. So we can't really afford to have an impact on latency. That means the going consensus is, if you want deterministic behavior, if you want 100% guarantee, you really need to allocate 100% of the required resources for your request. So this is basically where we identified a query with binary search, which would accurately point out to some extent what your container needs based on the usage. But that's just one part of the story. What we actually did was to, let's do a series of experiments and based on varying use cases, based on needs for those critical applications, even then reduce the request by as much as 75%. That's basically what we did. And on the right, it's not visible much, but basically on compute on the edge, we reduced the hardware by as much as 50%. So reduced it by half, the energy reduced by half, the real estate reduced by half, with increased performance and stability. So that's what the graph shows. So basically before the optimization, what we had was due to throttling and all sorts of behavior, we had very high contention going on, and then after and during when we shared the idling resources by reducing the requests, we had more of a smooth, balanced pattern with improved performance. Now, as well, we had massive effect on throttling. So obviously, we also expanded the limits a bit. Before we had what we assumed as to be deterministic, because of course we exclusively mapped all the resources, but actually it was on the downside, because in certain situations it needed more, but it couldn't get more. But now it could. Now this graph shows two things. On the left side, what is being shown is before we did the optimization. That means the request is completely allocated without changing the limits, where we had different sorts of sort of even sporadic behavior, not super stable. But then after we enabled it, basically we increased the amount of requests that got into the cluster by as much as 7x, while reducing the latency by close to 10 to 20%, and then of course reducing the cost by half. Now this was in practice, it's super simple, right? But then what was challenging, as he said, was really trying to understand all the assumptions that we make, and despite having all those things, for instance, what if the containers start to scale at the same time, and then we don't have enough resources because we are going to share everything? That was always coming into the picture because we wanted deterministic behavior, but we couldn't guarantee because we reduced it by as much as 75%. But the results showed otherwise, and then we went ahead with it. So I think that's a massive one. Now, to summarize the key takeaways, we have been talking a lot. We could have had way more points than this, but then to really summarize in 6 aspects, basically it starts with understanding your application behavior. Every application is different. The needs of them are different, and your requirements is usually mapped to the needs. So all of these, and the load profile, the user profile, everything is different. So usually don't go with the defaults. If you do, completely understand your application. And of course, the same thing goes for the JVM itself. So as well, try to limit the threats as much as possible. Also, you don't. The contention could be quite sneaky, and it's hard to identify. And what worked for us, I will leave it to you. But what worked for us is, despite having mission critical applications, we still chose to share the resources with an assumption, which we validated through multiple series of experiments, that not all workloads are going to peak at the same time. It's a very basic assumption, but if it failed, we would have massive consequences. But since our results proved otherwise, we still went ahead with it. So basically, we shared most of the cluster for all the workloads. And for non-critical applications, we basically just put a request to as low as possible and shared 99% of it. And obviously, the next one is to it's never a one-off. Whenever we configure things, we have to constantly monitor, fine-tune, adapt, and then repeat it. And as he said, we can't aim for a fixed target. It would never work, because a target would be based on the needs. You have to balance a list of trade-offs. So ideally, it's good to understand what kind of efficiency you are looking for, which is still balanced. Now, finally, again, scale based on application-specific behavior instead of just relying on default behavior, like relying on CPU utilization to scale out. That's mainly it. Thank you.
Time for questions. Yeah, go ahead.
So we often have the case that the cluster node is unavailable. For example, an upgrade or it's shutting down due to the load process. So you lose, let's say, one node completely, and then the scheduler says put all the continuous schedule all around. But then you deal with, for example, quotas, like you have, for example, you cannot put so much CPU limits on the namespace in one node, and then it comes that your application is only one of 2 instances becomes available for a longer period until all is shuffled around.
Okay, to repeat the question for the recording, there are scenarios when we don't have a node available and we cannot set the CPU limits at the namespace. And how do we deal with it? Right?
We have quotas for the namespaces.
Yeah.
And then due to all quotas, just say, hey, let's double the amount of CPU limits. And this is contrary to the namespace
Policy. right? I think the policy at the namespace and node level, they have to go hand in hand if we do CPU over commitment or not. So then should fit this scenario as well, and also when we don't have some of the nodes available.
Ideally, you should have some sort of a backup. It will never work if you just have one extra node. And then with conflicts, of course, you run a risk of constantly just looping and trying to place pods.
All right. Any other question? Yes.
Can I make 2 questions?
Sure.
First one. Great talk, by the way. You were very thorough when testing different servers, Tomcat, Ajith, but I didn't see anything about reactive applications, which in theory should be more stable for this line. Have you done any testing with that?
Okay. The first question is, we look at the servlet container performance. What about reactive applications? We use reactive for the web client communications, for example. There, we heavily rely on, and for example, for the data streaming, yeah, we try to leverage it there. So these are the main use cases where and then we improved also on the resource utilization. Compare, for example, with other clients that we were using before.
Any comparison with the other servers?
No, not that I'm aware of, but we can check after the talk.
The other question is, you mentioned testing native applications to startup.
Yeah.
Going with that because we had some issues.
Yeah.
What issues?
Well, our applications are heavy on business logic, and we have some monster library that we depend on. And then we are not comfortable to run those libraries in native mode. And then even if we qualify it now and then it's green, then later, if there will be another developer that will try to extend it, we need to be aware upfront, okay, in which scenario we are, because then we may end up in class not found in production, and is not desired.
And to add to that, we have dynamic workload, which is really not deterministic. I think things change way often, quite in the opposite direction. And then pre-compiling to native does not always materialize in good results because JVM as well learns from the heuristics of how things move. Yeah.
All right, thanks.
Thank you.
See you around and enjoy Spring.io.